Problem 37, page 685. We have a thin rod of length L. Thin rod of length L, so we are talking about the linear charge density. And a uniform charge per unit length lambda. When the distribution of the charge is uniform, so lambda is constant. If the distribution of charge is not uniform, lambda will be not constant. So we have lambda, the rod is along the x-axis. The question is, show that the electric field created at the point P, which is located at a distance D, as you see, the vertical D passing at the point O at the midpoint of the rod, shows that the electric field created at the point P has no x component. So we have to show that Ex equal to 0 and is given by, and E at the point P is given by 2ke lambda sine theta 0 divided by D. Be careful here. Sine theta is opposite to the length L over 2. Here we have L, and here we have L over 2. And if you say here R, for example, R square equal D square plus L square divided by 4. Okay. First of all, let's show the x component to find the solution that the x component is equal to 0. In general, x component equal to 0 or y component is equal to 0 when we have a symmetry. Yani by symmetric, you can find the result. Let's do the symmetric explanation. By symmetric, it means this rod is divided to two portions, to the right and to the left. Okay, to demonstrate the symmetry, we have to take a portion at this side and another one to the other side. The blue one, this small dq, creates at the point P a field E. We can say here E has two magnitudes, EY and EX. Here we have E, so EX for the blue, we can say blue, and here we have EY blue, and here we have E blue. For the red, we have, let's say, we have E. This one is E red with two components. We have EX component and EY component. Here, E red X component, and here we have E red Y component. You see here the, excuse me, here it's X component, and here it's Y component. Okay, so here we have X blue component, and here we have EY blue component. As you see here, the X components of these two values are opposite. So we can cancel the X component. Now we can say by symmetric, the X component EX must be equal to 0, as we see here, the X component. But the Y component is directed in the positive direction. So in general, the total E must be equal EY in the direction of J. This one in general, okay? In general. Okay, let's start to solve the problem. And you can say here we have DEX, DEY, because we are talking about a small portion. And also the final equation, you can say E equal EYJ. Okay, it's the same. Let's start here. So we finished the demonstration of the symmetric problem. Now let's talk only this one. Okay, here what we have a small charge dq. dq has a length dx because we are on the x-axis. Here we have dx. This one has an angle theta with the vertical. Okay, we said the steps we have to follow. First of all, we take dq. Second, we location or position. We have to precise the position of dq. Its position in function of O. It's located at a distance, we can say x. Here we have x, the height equal to d, and let's say here we have r. Okay, so d e equal plus d e y and j direction. Okay, let's draw here the y component. Here we have dy with the angle theta here. So this one is angle by opposite angle, and we can okay. So equal dey. If you take this triangle, dey, it's here, is adjacent to the angle. So cosine theta. Dey equal de cosine theta j. So de equal, we do the integral. So we do the integral of de equal the integral of like this. We do the integral here and the integral here equal de cosine theta g. The integral of de equal to e equal de equal k dq cosine theta j integral divided by the distance square between the point P and the located small element, which equal to R, equal to R. Okay, now we cannot put here the limit. Why? We have many variable parameters. Look, if we change the position of dq from here to here, from one extremity to another extremity, what's happening here? You will get R will change. So we have to substitute the value of R. The angle theta will change between this point to theta equal to 0 to this point, which is equal theta 0. As you see here, we have the angle of theta 0 at the maximum angle. And so theta will change by moving the small element. So we have to calculate the values of cosine theta here and R and dq. R equal, or R square equal, if we take this triangle, you know, this triangle, this one, and this one, R square equal D square plus X square. So equal D square plus X square. So R equal radical D square plus X square. And dq equal lambda dx. Okay, we have dq, we have r, and we have cosine. Cosine theta, if we take this triangle, cosine theta equals the adjacent side d divided by the hypotenuse r. So cosine theta equal d divided by r, which is equal to x square plus d square. Okay, we can write now the final equation of E equal k is constant. We can put it here. Okay, let's equal k, dq equal lambda dx, this dq, cosine theta equal d divided by x square plus d square divided by r, which is equal to radical x square plus d square. All these values in the direction of j. It's okay. You know that k is constant, lambda is constant, d is constant. The perpendicular from P to the point O will not change. It's constant. We can write dx divided by these two values. Listen, let this value equal to a. Okay, equal to a. If you say a times a half, or radical a times radical a is equal to a power 1 times a radical half is equal to a 1 plus half equal a 3 over 2. So we can write here equal a equal x square plus d square power 3 over 2. Listen, this integral, I give you its solution. You don't need to calculate its value, okay? Let me see. The solution of this integral of this one equal x divided by d square radical x square plus d square. Okay, so we substitute its value. We can say E equal k lambda d. But before, you see here we have only x as unknown. Okay, here we have x unknown. We have to put the limit of x. How can you find the limit of x? By moving the small charge from between the extremities of the rod. It means from this point to this point. If the charge is at this point, the distance is equal from here to here equal minus L over 2. Because it's the left of the center O. And in the case where the object, the element at this point, the distance is equal to L over 2. So the limit must be between minus L over 2, x equal minus over 2, L over 2, and plus L over 2. Here we have the limit of x. Okay, we can write the final equation. E equal k lambda d integral minus L over 2 plus L over 2 dx. Okay, we have the solution. So we can write d, we put the solution of the integral. Okay, we'll get x divided by d square radical x square plus d square between minus L over 2 and plus L over 2. Listen, it's important to know if we have an integral between minus a to a, you can, okay, in function of dx is equal to 2 integral from 0 to a. You can write this. So we can put here, instead of minus L over 2, you can put 0. And here you have 2. Here you put 2. Okay? It's important. So this is the final equation. We substitute L over 2 by its value. We put the value of x by L over 2. We can say here E equal to k lambda D, you know that X AB equal B minus A. Okay? So here we have L over 2 divide. We can put D square out. It's constant. Divided by D square. L over 2 radical X square. We substitute L over 2. We have L square over 4 plus D square. Okay, this is the answer in the direction of J. We have to find, don't forget, we have to find this solution of E. Not yet. Okay, we have to change to find this form of the electric field. What can we do? Okay, so here E equal 2k lambda d. We can cancel d by d. You will get d here, and up you have 2 and 2. We can cancel 2 by 2. You will get L divided by radical L over 2 square plus d square. Be careful here. We calculated, we put L over 2 by x, and here by its value. You have to put here minus. If you put 0 by its value, you will get 0 here. So you don't need to calculate its value here. Okay. In the direction of J. You know that sine theta 0, sine theta 0 equal here, sine theta 0 equals the opposite side L over 2 equal L over 2 let me see. We don't have 2 here because we canceled 2 by 2. Okay, L over 2 divided by this, divided by, we can say here, R prime. Okay, R prime equal radical L over 2 square plus D square. Okay, if you take the triangle here, this triangle, this one. So this hypotenuse equal L over 2 square plus D square. Okay, we can say here sine theta 0 equal L over 2 So we calculated E value, it's like this, and we said that sine theta 0 equal L over 2 divided by R prime, which is equal to L over 2 square plus d square in this triangle. Okay, so we need to, as you see here, we have to find this result. We need to have sine theta 0 in the equation. In this case, we can multiply by 2 and divide by 2. Nothing changed. And so L divided by 2 times this value is equal to sine theta 0, equal to this one. So E equal to KE lambda sine theta 0 J divided by D. Okay, it's okay. Excuse me, here we have lambda. Here we have lambda in the problem. Now, part B, in the problem, if L equal to infinity, show that E is equal to 2 KE lambda over D. We have to find this one. You know that theta 0 is the angle between the vertical position and the extremity of the rod. So if we increase the rod to the infinity, so the angle theta 0 must be equal to 90, because the rod in this case goes to infinity. And here the infinity of this line will extremely touch the end of the extremity of this rod. And the same here, if you take this one to the infinity, if you want to join the point P with the extremity, you will get also a line like this, extreme like this. Yani it's equal to 90. Okay, in this case, we can say here, in this case, E equal to 2 K E lambda sine 90 divided by D, which is equal to 2 KE lambda over D in J direction. Okay, this is the answer. Thank you.